Once you've found a general solution to the wave equation using separation of variables, it's time to find a particular solution. In other words, pin down those arbitrary constants to satisfy an initial condition. So here I'm just going to describe what an initial condition to the wave equation has to look like and how you can use those to determine the coefficients in the eigenfunction expansion of the solution to the wave equation. Okay, so the wave equation has two space derivatives and two time derivatives. The two space derivatives are handled by boundary conditions, that is, specifying the value of u at 0 and L, and that would be a Dirichlet boundary condition, or specifying the slope of the function at 0 and L, and that would be a Neumann boundary condition, or a combination thereof. There's a whole bunch of different scenarios. But here, what we need to do is figure out how to handle all the additional coefficients that crop up because of the two time derivatives. And that's much like a second order ODE in which you have two initial conditions. You have to specify y naught and v naught, let's say. And so in this case, what we're going to do is we're going to specify the original shape or the initial shape of the function and the initial velocity. So that's if u is the deflection of, let's say, our guitar string. So here we have a guitar string that's pinned down at the ends. That gives me Dirichlet boundary conditions. And we have some initial shape, let's say like this, where u is the vertical deflection of the string from the neutral position. So that's what u of x and t is. And so, or let's say that there should be a 0 in there. So that is going to be specified by v of x. And then if you just let it go, then the initial velocity of the points on the string at every point will be 0, and it just accelerates from that 0 velocity. But you could also start off sort of pushing the string or launching the string off in a direction, and that would give it some initial velocity g of x. And so these are the initial conditions that we're going to use to specify all the constants in the general solution. So let me write down the general solution again. And this was covered in a previous video on the playlist. So we have a sum from n equal 1 to infinity of Pn, let's put a bracket up front, cosine Cn pi over Lt plus Qn sine Cn pi over Lt times the sine of n pi x over L. And so because we're satisfying, okay, this was the general solution for the case where we have homogeneous Neumann boundary conditions, homogeneous Dirichlet boundary conditions. But a similar thing would be true if we had homogeneous Neumann boundary conditions. We would just change the sine to a cosine and proceed similarly. Okay, so u of x and 0, when I do that, I plug in 0 for t, and the cosine term turns to a 1, and the sine term turns to a 0. So we have the sum from n equal 1 to infinity, Pn sine of n pi x over L. And so that has to be equal to f of x. So the Pn are going to be determined by an odd periodic extension of f. Okay, that's what our first boundary condition does for us. And then now if I take a time derivative of our original, and this is for the sake of on the next line plugging in t equals 0, now I get the summation from n equal 1 to infinity of, and now to save myself some space, because I know I'm going to be plugging in t equals 0, here I'm going to have a whole bunch of stuff and a Cn pi over L multiplied by Pn, and there'll be a minus sign in there too, sine of Cn pi t over L. But that t is going to be 0 in a second, and this whole term is going to disappear. So I'm not going to spend too much time writing all the details, but on this one we have a plus Cn pi over L Qn, and then this is going to become a cosine Cn pi over L times t. and that gets multiplied by a sine n pi x over L, which is unaffected by a time derivative. And then when I plug in t equals 0, the pn's disappear, and I'm left with the sum from n equal 1 to infinity of cn pi over L qn, and the cosine becomes 1 because I'm plugging in t equals 0, and I'm left with sine of n pi x over L. And so this has to be equal to g of x, which is the initial velocity of the string at every point. And we have again a Fourier series, but I'm going to call this, let's say call this Bn. So the Bn are going to be the Fourier sine series. So Bn are going to be determined. So I'll just write this. This is the same sentence, but with Bn in front and g at the end. So determined by odd periodic extension of g. And so that's how you find your Bn's. You use the formula for Bn's, but then Bn is Cn pi over L times Qn. So we need to ultimately get our Qn's, which is going to be L over Cn pi multiplied by whatever we calculated the Bn's from the Fourier series calculation. So the Pn's will have some formula like 2 over L integral from 0 to L of f of x sine n pi x over L dx, and the Bn's will be the same thing for from 0 to L of g of x sine n pi x over L dx, and then we get the q, so just copy that down here, and that's how we get Qn. So that gives us the Qn's, the Pn's, and the Qn's, which can then be plugged in here, and we've gotten rid of all the arbitrary coefficients, and we can now write down a final particular solution to the initial value problem, wave equation with boundary conditions and initial conditions.